All right, good morning. So let's get started. In the previous class, we talked about typical sequences and joint typicality, and we saw some properties of jointly typical sets. Right. So we defined mu a b of x and y n's as the empirical frequency or the fraction of times the pair a b occurs in x and y n. Right? And a typical set is one where all the empirical frequencies are close to the true probabilities. The fraction of occurrences of every pair of symbols is close to the joint probability of occurrence of that particular pair of symbols. All right. So similarly, we can also define the conditionally typical set. So given xn, given a particular sequence xn, we define this conditional typical set as in a very similar fashion. So it is a set of all yn which are jointly typical with respect to xn. So yn is in the conditional typical set corresponding to xn if and only if xn and yn are both lie in the jointly typical set. So this is the conditional typical set for a given xn, whereas this is the jointly typical set. So in the previous class, we saw some properties of jointly typical sets. In particular, we saw that the jointly typical set is a high probability set. The probability that a random pair of sequence distributed IID according to Pxy. So the probability that this is not in the jointly typical set is exponentially decaying in n. So this is less than or equal to e to the minus some constant times n, where this constant depends only on Pxy and epsilon. So more explicitly, we can write this as, so it is less than or equal to some e to the minus alpha n epsilon square, where the alpha depends only on Pxy. All right, and we also saw some more properties. So for any pair xn yn in the jointly typical set, the probability of occurrence of that particular pair of sequences is close to 2 to the minus n times h of x comma y. Right. So the probability of occurrence of that particular pair is close to 2 to the minus n times the entropy, and we also saw that the size of the jointly typical set is close to 2 to the n raised to entropy of x and y. All right. So we can prove other properties as well, particularly for the conditional typical set. And one interesting property is that if you have two sequences which are jointly typical, then individually also they must be typical. All right. So in particular, if xn, yn are in the joint typical set T epsilon n of Pxy, then xn should be in T epsilon n of Px, and yn should also be in T epsilon n of Py. So in this class, we'll see some interpretation of what this means for a very specific joint distribution. And then we'll go on to prove some more properties of typical sets, jointly typical sets, and conditional typical sets. And maybe in the next class, we will prove some more results using these. So far, we're only looking at these, at the properties of such sets, but then we will use these properties to prove channel coding theorems from the next class onwards. Okay, so but before we proceed, are there any questions? Any questions? Okay. So let's see some geometric interpretation of these notions of typical sets. And we'll restrict ourselves to just the binary space. So let's look at binary sequences xn and yn, and see what happens. All right. So to understand this better, it's helpful to think of some notion of distance between sequences. Now, the geometric interpretation that we'll use here, so we can't really visualize binary spaces very well. But then so I'll draw some diagrams which will give some kind of geometric intuition, but this is not exact in the sense that what I draw over here doesn't really correspond to binary space. Where our brains are more hardwired to think about Euclidean spaces and Euclidean distances and not really Hamming distances, but the analogies will be very similar. So you can and the intuition is basically going to be the same. Okay, so over this binary space, I'll define a distance between a pair of sequences or between any 2 points in 0, 1 to the n. So this is called the Hamming distance. You may have seen this previously. So the Hamming distance between any pair of sequences is the number of locations in which the two sequences differ. All right. So let's take an example. So let's say that xn is this sequence 1 0 1 1 0 1, and yn is the sequence or 0 1 1 0 1 1. Okay. So how many locations in which are there where these two sequences differ?
4.
In 4 locations, right? So they differ in this location, they differ in this location, they do not differ in this location, they differ in this location and in this location. Right? So the Hamming distance between this particular xn and yn is equal to 4. Right? So given any pair of sequences, you can compute the Hamming distance. And this Hamming distance can be defined over any space, right? Not necessarily just binary space, and we'll see the Hamming distance in many problems. So similarly, we also define the so-called Hamming weight as, in one way, this can be defined as the Hamming distance between xn, between so the Hamming weight of a particular sequence xn is the Hamming distance between xn and the 0 vector, right? So can you tell me what this will be equal to in terms of xn alone? So in particular, if I look at say 0 1 0 1 1 1, what will be the Hamming weight of this particular sequence?
4 non-zero.
Right, exactly. So this is equal to 4, and the Hamming weight is basically the number of non-zero locations or the number of non-zero elements in xn. Right, so that is the Hamming weight. Okay, and it's possible to verify that this is indeed a distance in the sense that firstly it is equal to 0. So the Hamming distance between any 2 points is equal to 0 if and only if the 2 points are the same, xn equal to yn, and it's always non-negative, and it is symmetric. So the Hamming distance between xn and yn is the same as the Hamming distance between yn and xn, and also it satisfies the triangle inequality. So given any 3 points xn, yn and zn, the Hamming distance between xn and zn is less than or equal to the sum of the Hamming distances between xn yn and yn zn. Okay, so this is indeed a metric, and so we can kind of interpolate between this and the standard notion of Euclidean distance that we can visualize more easily. Okay, so we want to understand typical sets using these notions of Hamming distances and Hamming weights. Okay, so let us consider the following joint distribution Pxy, which is obtained in the following manner. So x, the random variable x, is, let's say, Bernoulli q for some q between, say, 0 and a half. Okay, so I'll pick two numbers, p and q, which both lie between 0 and a half. Now, there's no real reason to have it exact. It can also be anything between 0 and 1, but let's keep it between 0 and half, because otherwise it's generally symmetric. So so I generate an x. So the random variable x is Bernoulli q, and y is obtained by passing q through a BSCP. So given a particular q, you generate, so given a particular x, you flip x. X could be either 0 or 1. So you pass x through a BSCP, or in other words, you flip x. You convert 0 to 1 or 1 to 0 with probability p, and then you leave it as it is with probability 1 minus p. Okay, so that is my joint distribution Pxy. Okay, so x is going to be Bernoulli q, and therefore y is going to be some Bernoulli r, right? Where what is r equal to in terms of p and q? What is the probability that y is equal to 1?
Y will be P star Q, right? Where
Right.
P star Q equal to P into 1 minus P into Q.
Yeah, so this is p star q, which is p into 1 minus q plus q into 1 minus p. Okay, good. So this is what y will be. Okay, so let's see what this means. Right. So we know that from the properties of typical. So now suppose that we have we define the typical sets corresponding to pxy and px and py. Okay. So let's look at the typical set corresponding to px. Right. So by definition, so it is the set of all sequences xn, all binary sequences, for which mu0 of xn is close to 1 minus p, and mu1 of xn is close to p. Right. So in other words, the fraction of zeros is close to 1 minus p, and the fraction of ones is epsilon close to p. All right. So what does this say in terms of the Hamming weight? So what can you expect the Hamming weight of xn to be close to?
So it will be N into P.
Correct. Right. So it will be close to n into p. So more precisely, this will be equal. So this will be between 1 plus epsilon 1 plus epsilon np and 1 minus epsilon np. So it's 1 plus or minus epsilon close to n times p. Right. So if you think about it visually, I mean, although I'm interpolating this to Euclidean space. So given the zero vector, so suppose that this is the center of my Hamming space or binary space, my xn's are all going to have Hamming weight close to n times p. Right. So if you think about it, they're going to lie in some small region. So if you assume that this is the distance from 0, the Hamming distance from 0, then they're going to lie in some kind of a thin shell, which is between 1 minus epsilon np and 1 plus epsilon np. So all my xn's are going to lie in this thin shell. They're all going to lie in this particular region. Okay, and similarly we can define the typical set corresponding to py, t epsilon n of py. And so this is going to be, so this thin region is going to be t epsilon n of px, roughly speaking. And similarly, you can also define the typical set corresponding to py. So what can you say about the Hamming weight of the sequence yn for any yn in the typical set? Yes, anyone?
One plus or minus epsilon whole into np star q.
Correct. So it's going to be close to p star q, right? So if you think about it geometrically, it's going to lie in another thin shell. So all the yns are going to lie in this thin shell, and that is going to be, so this, so this set is going to, so t epsilon n of py is going to look something like this. It's going to be some thin shell, which is between 1 plus epsilon times n p star q and 1 minus epsilon n times p star q. Okay, so individually xn is going to lie in one thin shell, and yn is going to lie within some other thin shell. Now you have to be a little careful, although I'm drawing these pictures using this is actually Euclidean geometry, but Hamming geometry is also, or in binary space it's going to be similar, but this is just for the purpose of visualization. Okay, so these are what you can imagine these typical sets to be, right? So individually xn is going to lie within some thin shell, and yn is going to lie within some other thin shell. Okay. Now what about the joint distribution of x and y? So given one particular xn, so let us fix any xn in the typical set. So you know that if xn, yn are jointly typical, then xn and yn are individually typical with respect to each other, right? So you know that every typical xn is going to lie within this particular thin shell. So let us say that this is one particular xn. Now conditioned on xn, so having fixed the particular xn, what do you expect the Hamming distance between xn and yn to be? So remember that yn is obtained by passing xn through a BSCP. So you're flipping each xi with probability p. Right? So what do you expect the Hamming distance between xn and yn to be?
Roughly n times p star q minus p, we can say, right, sir?
Not really. So think about it. So you fix an xn, right? And what is the Hamming distance? The Hamming distance is the number of locations in which xn and yn differ. And basically you're flipping each xi with probability p, right? So you're taking xn and you're flipping each xi independently. So really the Hamming distance is basically the number of locations in which xi was actually flipped, right? So what do you expect this to be? What do you expect it to be close to?
Then NP only it will be, right?
Exactly, it's going to be close to NP. So I guess your intuition as to why you said something like n times p star q minus n times q, right? So that is not really correct because the Hamming distance between xn and yn is not equal to the difference between the Hamming weights of xn and yn, right? Because even in Euclidean space, the Euclidean distance between two sequences is not the difference between the norms of xn and yn.
Yes, sir.
So yeah, my apologies. This should have been n times q and not n times p for xn. So you expect that yn is going to lie within some ball, right? It's going to lie in some region around xn. Right, so conditioned on one particular xn, yn is going to lie in some region which looks like this.
Sir,
Yes.
sir, can you please repeat this argument once?
Yeah, just one second. Yeah. Okay. So let us fix any xn in the typical set. In fact, take any xn, irrespective of whether it is in the typical set or not. We want to know where yn will lie with respect to xn, with this particular xn. And we know that yn, if it is typical, it's so the typical behavior will be as though you passed xn through a BSC P, right? So you're flipping each bit of xn independently with probability p. All right. So which means that the expected number of locations in which xi differs from yi will be close to n times p. All right, or the Hamming distance between xn and yn will be close to n times p. Mainly because you're flipping each xi with probability p, and basically the Hamming distance is the number of locations in which the two sequences differ, right?
Okay, got it.
Right. So given an xn, you obtain for a fixed xn, yn is going to, if you pass xn through a BSC P, then you would expect to see yn lying within distance close to n times p. So this distance is going to be roughly n times p.
Yes, sir. One more doubt.
Yes.
Sir, but maximum is NP, right?
What maximum is NP?
Yeah, maximum distance, Hamming distance between xn and yn.
No, it need not be maximum, right? So what will be, in what case do you say that the maximum will be n times p?
Every bit is flipped then.
Correct. So every bit is flipped with probability p.
Yeah.
So with a very small probability, it could be much larger than NP, right?
Yes, sir. Very small.
Because there is some probability that all the bits were flipped, but that probability is very, very small.
Yes, sir.
But with very high probability, it is going to be close to n times p. Basically, what are you doing? You're just tossing a coin, right? And with probability and the probability of it being heads is equal to p, right? So with high probability, you're going to see roughly np heads, or in this case, np ones, or np flips. Correct?
Yes, sir.
So that is really what is happening. So conditioned on an xn, the yn is going to lie within distance close to n times p. Okay. Now this is for a fixed xn, and you know that yn is going to lie within some thin shell over here. So if xn and yn are jointly typical, then so for this particular xn, the conditional so this is going to be the region where xn and yn lie. Right?
Sir, what does that epsilon imply, sir?
So the epsilon is basically just some tolerance, right? Because of course you can't make it exact. You can't say so. Okay. So let us say that we're tossing coins, right? Or you're generating Bernoulli random IID Bernoulli random variables. You know that the number of ones is going to be close to whatever n times q if each bit is Bernoulli q, right? So it is going to be close to n times q, but in any case you will not see that it will be exactly n times q, right? The probability of that happening is very, very small. But then even if you sort of deviate from nq by a very small amount, so nq into 1 plus epsilon, nq into 1 minus epsilon, then this is going to be, then that set is going to have overwhelming probability. And basically the epsilon just represents this. It is some small tolerance. You have to give some small tolerance from np or nq such that you can see that with very large probability the sequence is going to lie in that particular set. Okay. And in fact, this analogy also will extend to Euclidean space. So if you take a Gaussian random variable, or basically a Gaussian random vector with IID Gaussian entries, a Gaussian with mean 0 and variance sigma square, then with very, very high probability, the norm of this Gaussian random vector is going to be very close to n sigma square, right? And that is basically what is happening over here. So in fact, you can just replace this with the following setup, where x is Gaussian with mean 0 and variance sigma square. You pass it through an AWGN channel. So maybe x is Gaussian with mean 0 and variance, let's say p, and AWGN with variance sigma square. And you look at y, then x is going to lie within some small shell of radius np. Yn will lie in some thin shell of radius n times p plus sigma square, and conditioned on an xn, yn is going to lie within some other thin shell of radius sigma square from xn.
Sir, one more doubt, sir. Sir, are we just considering the case where every bit is being flipped?
Exactly. Every bit is flipped with some probability. So,
yes.
So every bit may not be flipped, but basically, let us say that you take 1 0 1 1 0 1 1. Suppose this is my xn. Then I generate a Bernoulli random variable q, or Bernoulli random variable with probability q. So if that is 1, then you flip this, and maybe with probability 1 minus q, you just leave it as it is. Right. So this could be.
There can be possibility that other codes can be possible, right? Where all bits may not be flipped.
Correct. But so that is why we are looking everything in a probabilistic fashion, right? So So that is what we're doing. So we define these sets. So let us look at just xn. Now xn can take any value. It can be any binary sequence, right? In general, xn can be any binary sequence. But if you look at this particular set, which is basically a thin shell with Hamming weight between 1 minus epsilon nq and 1 plus epsilon nq, then the probability that xn lies in this particular shell is going to be very, very large. Right? So it's possible with some small probability it could lie outside the shell also. It can lie anywhere in Hamming space, but the probability that it lies in this shell is overwhelmingly large. As n becomes large, the probability that it lies in this shell is very, very large. And that's just a consequence of just Chernow's law.
Yes, sir.
And that is the only point over here. So you look at these shells. So in general, xn and yn can lie anywhere in this space. But what we are interested in is those regions where xn and yn are tightly concentrated. So where is most of the probability going to occur? So with very high probability, xn is going to lie in this particular set. With very high probability, yn is going to lie in this particular set. And given one xn which lies in this set, yn is going to lie in this particular set. So this is going to be, so these are the typical sets. That's why they're called typical, because with high probability, they're going to lie in these sets. But of course, I mean, there's a non-zero probability that they lie outside this set, but the probability that it lies outside these sets is very, very small. And so those are events that we're not really very interested in. The real events of interest to us are the typical events, and the typical event says that they're going to lie in these small sets.
Okay, sir, got it.
All right. And these sets have much smaller volume than or size than the entire space. Right? We know that the size of this typical set is 2 to the n times h of x, which could be much smaller than 2 to the n, because h of x could be something much smaller than 1, right? And similarly, this typical set could be much smaller. Yes.
Sir, then like a sequence y belongs to this red color region. Is the with probability is then 1 plus minus epsilon n into pq, right?
Sorry?
Like a sequence yn that
Yes.
belongs to that red color region that is
Correct.
marked in the picture.
Correct.
Has probability is n into plus minus n into in bracket 1 plus minus epsilon into pq, right?
Why do you say that is a probability of occurrence?
Because like and y belongs to this red color region is like is given like y belongs to a typical region given y x is also a typical sequence, right?
Yes, but there wouldn't be n times pq, right? So the probability that you see a particular y given a particular x is going to be whatever. So you can compute the exact probability. So the exact probability that yn equal to some particular yn given that xn is equal to xn. Now again, I leave this as an exercise, but this is going to be p raised to the Hamming distance between xn yn times 1 minus p raised to n minus the Hamming distance between xn and yn. And that is really because so the probability that you see this for this particular yn to occur, given that this particular xn was sent to the input of the BSC, so this happens if exactly dh of xn yn locations were flipped and n minus dh locations were not flipped.
Yeah, that I
Right?
understood. But yeah, that I understood. But what happens is probability that so then that red color region is the jointly typical region, right?
Yes, it is a jointly typical region.
Okay, so then y belongs to that jointly typical region, given y x is a typical region, x
Correct.
in typical region.
So really the conditional typical set is going to be in fact something like this region. So the set of all points which are at a distance np from xn is going to be this set over here.
Correct. Yeah.
But in fact, so again, this is the difficulty with visualizing high dimensional sets. Uh, you will see, I mean, if you do a very careful analysis and think about it, in fact, most of the probability will lie in this particular red region, although it may not seem so from this picture, because after all we can draw is for 2 dimensions. You will see that most of the probability will lie in this red region over here.
Just like most of the xn belongs to the typical sequence.
Exactly. So,
Typical
so
region.
something of that sort. Yes.
Okay.
Because for x and yn to be jointly typical, both xn should be typical and yn should be typical, and yn is typical if it is in this region over here. So the intersection of these two will be in this red region.
Okay. Okay. Yeah. Got it. Yeah.
Right. And of course, from this picture, it may seem that actually no, most of the probability lies in this region, but again, this picture is for 2 dimensions. In high dimensions, things behave very differently. So a very surprising property of n-dimensional space is that now, if you look at a sphere, okay, now this is a very interesting consequence and is not and it is not intuitive at all. But if you look at at very high dimensional space and you look at a ball of radius, say np, right, or ball of radius square root np. So you look at Rn and you look at the ball of radius, say square root np. Xn is less than or equal to square root np. So in fact, this is going to be whatever, some ball, right? You look at where most of the volume of the ball is concentrated. You will see that most of the volume of the ball is in fact concentrated near the surface of the ball. So basically, if I look at the volume of this, volume of Bn of square root np, and I remove everything else in between, right? So I remove a huge chunk from between. So that is volume of Bn of square root np into 1 minus epsilon. So really, I'm removing most of the region from within the ball intuitively. You'll see that the volume remains roughly the same. So this will be very close to the volume of Bn of square root np. This holds for very large dimensions. So even though in 2 dimension it appears that most of the area of this ball is somewhere in between, right? But for very high dimensions, most of the volume will be concentrated near the surface. Right? And again, that's because we cannot visualize high dimensional space, but you can do this calculation yourself. So you can just look up Wikipedia and find the expression for the volume of a ball of radius square root np and the volume of a ball of a radius square root np into 1 minus epsilon, and then find the difference between these two, and you'll see that as n tends to infinity, the difference between these volumes is actually is that this volume is going to be very, very much smaller than this volume. All right, so in fact, the volume of Bn of square root np, this is pi raised to n by 2 divided by the gamma function n by 2 plus 1 square root n by np whole raised to n. And this gamma function is something which grows as n by 2 raised to n by 2. And you can do the, I would encourage you to do this calculations on your own, and that is, and you'll see that most of the volume is in fact concentrated near the surface of the sphere. But that again, it's an artifact of very high dimensional space, and this is something that you would see in a course on, say, high dimensional probability or whatever, theoretical data science in some sense. And really something similar is also happening over here for very high, we're interested in very high dimensional space, and this is what the geometry looks like. Okay. Any questions? So it takes a while to get this sort of intuition. It is not obvious, and the only way to get this intuition is to try and calculate these probabilities yourselves. So take an xn, yn. So find out what is the probability that xn lies. If you take a Bernoulli sequence xn, then what is the probability that it lies, or what is the probability that the Hamming weight is between 1 minus epsilon and 1 plus epsilon? You see that that's very, very large. And similarly, what is the probability that it lies in this thin shell over here? What is the probability yn lies in this particular thin shell? You'll see that it's very large. So given an xn, what is the probability that the Hamming distance is close to np? That is also very large. So if you try to think about it geometrically, this is what the intuition will be. All right, and this intuition is very helpful when you try to design codes or when you try to think of channels, because this is very high dimensional space, and trying to develop this intuition is very useful and very important, because otherwise it becomes just a sequence of mathematical steps which you think don't have any meaning. But in fact, almost all of information theory has this rich intuition, but unfortunately all of this is in high dimensional space, so it takes a while to get used to this intuition and try to get this interpretation. All right. So that is why it's this notion of typical sets is very helpful, and particularly the two kind of vanilla examples of Hamming space as well as Euclidean space with Gaussian distributions. They probably give us the most intuition, and once you develop intuition for these two, more general channels become much easier to think about. All right, so that is why corresponding to each of these statements, you should try to develop intuition. So xn lies in the typical set means that, okay, xn is going to lie within some thin shell around the origin, and yn is also going to lie in a thin shell of a bigger radius around the origin, and this says that, okay, so what is the size of each shell going to be? It's going to be close to 2 to the n times the entropy. And the probability that it does not lie in the thin shell is decaying exponentially in n. And similarly, if you look at for a particular xn, what is going to be the size of the thin shell around yn. So basically, what is the volume or what is the size of this thin shell going to be? That is going to be 2 raised to n times h of y given x, and that is going to be, yeah, so that is going to be 2 raised to n times, roughly 2 raised to n times h of y given x. So it's helpful to just do these calculations, find out what each of these is going to be for, let's say, the BSc, and that already gives you a lot of intuition and geometric interpretation. All right, but at the same time, we should also try to prove each of these steps formally. Now, there are two things. There is one which is intuition, which helps you think about what the theorem should say. That is extremely important. But at the same time, we should also be able to formally argue using only mathematical steps to prove each of these statements exactly mathematically. Right? So there are sort of two faces of the same coin. So you need intuition to guide you to prove mathematical statements, but then to prove the truth, you need a mathematical proof. Right? Just intuition itself is not sufficient. All right. Okay. So, yes. Any questions? Right. Okay. So now let's look at another statement, which is again it comes very intuitively. Let us suppose that we take an xn which is in the typical set, right? T epsilon, say it's epsilon prime typical, or some small epsilon prime greater than 0. I take this xn, any xn. So you pick any xn from this particular region over here. All right, so let me maybe copy this. Yeah. So perhaps, yeah. Keep this here so that it helps with our intuition. So let us pick any xn. So pick any particular xn in the typical set. But this is note that this is some epsilon prime typical, or some small epsilon prime, and look at, okay, so what is the probability that a yn, so I take this xn, I pass it through a discrete memoryless channel, py given x, and I get a yn at the output. Note that xn is fixed, it is something from the typical set, and yn is now going to be a random sequence which depends on what exactly the instantiation of this DMC is going to be. Right? And now the question is, now I have a pair xn and yn. Now what is the probability that this xn yn lies in the typical set, right? So I take this xn. So yn is going to lie in this thin shell, right? Now, as I said, the jointly typical set is going to be, so if they have to be jointly typical, then yn should lie in this red region. Now, for a given xn, yn can in fact lie in this particular region, anywhere in this green region. But the question is, now, what is the probability that they're jointly typical? So what is the probability that yn in fact lies in this red region? And what this statement says is that yn is going to lie in the red region with overwhelmingly high probability. The probability that it is not in the red region is vanishingly small. Okay, but note that to prove this, again, so this is our intuition says that yn lies in the red region, but more formally, xn lies in the epsilon prime typical set, whereas xn, yn are going to lie in an epsilon typical set where epsilon is greater than epsilon prime. All right, and so let's see how do we prove this particular statement. So it is all kind of intuitive. According to intuition, given xn, yn, the Hamming distance between xn and yn is going to be close to n times p. But in addition to that, we have some more requirements for it to lie, for xn, yn to lie in the jointly typical set.
Sir,
Yes.
wouldn't it depend upon the probabilities? Like we are not considering anything related to probability currently.
We are, right? So the typical set is already incorporating the probabilities themselves, right?
Okay.
So it is only in the case for the, again, this picture that I've drawn is only for the case of the binary symmetric channel, or you can also, the same intuition holds for Gaussian channels as well, where everything can be stated in terms of the Hamming distance of the Euclidean distance. For more general channels, for more general alphabets, it's harder to visualize.
Okay. Sir.
So there you cannot state it in terms of just a distance alone. You have to in fact look at the probabilities themselves. And that is really what the typical set is capturing.
Okay, sir.
Yeah, so this is just intuition. So the picture over here is to just give us intuition, whereas this is the actual statement. So this should only be to guide us, whereas this is what we should really be following. Okay, so let us look at the proof. I will only maybe sketch it out over here. So look at any particular xn. So we know that xn lies in the typical set. T epsilon prime n of px. So what do we know? We know that mu, so for any symbol a, we know that the empirical frequency, the empirical probabilities is going to lie between 1 minus epsilon px of a and 1 minus epsilon prime px of a and 1 plus epsilon prime px of a. Okay, and what we want to show is that now if I pick a random yn, then mu ab of xn yn, the joint empirical frequency or the joint type of xn and yn is going to lie between 1 plus, so this is given. What we want to show is that for every a comma b, for every symbols a and b in the alphabets, the type, so this is the joint type of the empirical frequency, this is going to be in this. So this is what we want to show. Okay, and now again, so whenever you want to show something like this, you either just invoke the weak law of large numbers, or you use Chernoff bound. So one of these two. So the weak law of large numbers will say that just the weak law of large numbers is sufficient to prove this particular statement. But Chernoff bound will give us something tighter. We'll know that we'll in fact be able to show that this probability of that this happens actually decays exponentially in it. All right, and it's again very simple. So we want to know what is the probability of this not happening. So what is the probability that mu ab of xn yn minus pxy of a comma b is greater than epsilon pxy of a comma b. What is the probability that this deviates significantly, right? And for this we'll sort of split this into two things. So mu ab of xn yn minus py given x of b given a. We already know that the fraction of a's in xn is going to be close to px of a, right? And we want to know what is the probability that the fraction of b's in these particular locations is much different from py given x of b given a. So if we show that that probability is small, then we are done. Given a, px of a. Right? So one way is to, so let's just look at what is. So this is, we can write this as a summation I going from 1 through n. Again, we'll write this in terms of indicator functions. Indicator that x, so a comma b of xi, yi. We want to know how many locations xi is equal to a and yi is equal to b minus b of b given a times probability that x is equal to a. This is greater than epsilon times py given x of b given a times px of a. Right? But we already know that, so if there's a location where xi is not equal to a, then there is no contribution to this at all. All right, so let us define SA as the set of all locations I such that xi
Sir?
is equal to, yes.
Could you please repeat that last one?
So which, this statement?
Yes, sir. Yes.
So I've done nothing over here, right? So I've just said that. So what is mu AB? Right. So it should be 1 over n. So mu AB is the fraction of locations where xi equal to a and yi equal to b.
Yes, sir.
Right. And that I've just written it out in this way. So it is 1 over n times the number of locations where xi equal to a and yi is equal to b. So this indicator function AB of xi yi, this is equal to 1 if xi equal to a and yi equal to b and 0 otherwise. Right? So we saw this in the last class.
Yes, sir. Clear.
Right. So okay. So now let us look at the locations I such that xi is equal to a, because we only need to restrict ourselves to those locations. We know that since xn is typical, we are guaranteed that the size of SA is going to be between 1 plus epsilon prime n px of a and 1 minus epsilon prime n px of a. So this probability basically is, I can say that this is, so it's enough if I just restrict myself to the locations I in SA. All right. So in these locations, xi is equal to a. So I need to find out in how many of these locations yi is equal to b. All right. So p y given x of b given a Px of A is greater than epsilon times Py given x of B given A Px of A. Okay, so you know that this so you know that the expectation of this since the yi's are all conditionally independent and identically distributed in these locations, so this expectation is simply going to be size of SA times, so maybe there are m locations where xi is equal to A. So in these, if you look at the expected number of locations in which yi is equal to B, then it is just going to be m times the probability that y equal to B given x equal to A. All right, and the rest is just a matter of simplification. So we just use the Chernoff bound, and now you'll have both epsilon and epsilon prime, and some simplification is enough to show that this probability of error in fact decays as n tends to infinity, decays exponentially as n tends to infinity. All right. So we're kind of out of time. So I'll stop at this point. So you can just do the calculations yourself. It's not too hard, just a little bit of simplification that is required. So only steps that you need to do from this point onwards is to sort of simplify it to a suitable form and then use Chernoff bound. That is it. And you'll see that this probability is less than or equal to e to the minus n times some constant times epsilon minus epsilon prime the whole square. Right? So it's essential that epsilon is strictly greater than epsilon prime, otherwise this probability of error is not guaranteed to decay exponentially. All right. Any questions?
Sir, could you please repeat that expectation part? Underline.
Fine. So let's look at this term over here, right? So it's just the expectation of this sum. The expectation of summation I in SA indicator function B of yi, right? Which is just the summation I in SA expectation indicator function B of yi. But what is this equal to? So this function is 1 when yi equal to B and 0 otherwise. Right? So what is the expectation of this quantity?
The probability that y equal to b.
Correct. So it's the probability of y equal to b in regular term, in regular cases. But now we're only looking at those locations where x is equal to a, right? So that is why this is going to be summation I in SA, since we're looking at only those locations where x is equal to a. So the expectation is just going to be the probability that y equal to b given x equal to a. Right? And you can just take this out. You will just get size of SA times py given x of b given a, right? Is that clear?
Yes, sir.
Okay. Any other questions? Okay, so if not, then we meet in the next class. So see you until then.
Thank you, sir.
Thank you.